Hello everyone, in this video I'll be discussing some past years of MME-1. So mathematical methods for economics has been taught to first year econ students. Okay, now we'll start with the questions. The time in minutes t required for a rat to run through a maze depends on the number of trials. So time is a function of number of trials that the rat has practiced. So the function is given to us. How does the change in n impact the change in t? So we are supposed to find that is how t changes with respect to a change in n. Okay, I'll solve this. Okay, we have tn equals to 3n plus 15 upon n plus 1, where n is greater than equal to 1. Now the first order derivative, we will use the quotient rule. So first function, derivative of first function into second function minus derivative of the second function into the first function upon n plus 1 square. So this becomes 3n plus 3 minus 3n minus 15 n plus 1 square. This cancels out, so we are left with minus 12 upon n plus 1 whole square. So what we can see is this term, since n was supposed to be greater than 1, n plus 1 square would any day be greater than 0. And since we have minus 12 here, so this whole term is less than 0. So this means as the number of trials, the economic interpretation or the interpretation of this would be, as the number of trials increases, it would take less time for the rat to clear the maze. So if you will keep on increasing the number of trials, it would take less time for the rat to clear the maze. Now the second part, does there appear to be a limiting time in which the rat can complete the maze? Okay, so we are supposed to find the limit of Tn as n approaches infinity. So limit Tn as n approaches infinity equals to limit as n approaches to infinity 3n plus 15 upon n plus 1 upon n plus 1. So this can be written as 3 plus 15 by n as limit n tends to infinity upon 1 plus 1 by n. As n tends to infinity, this term would tend towards 0, this term would tend towards 0, so the whole term would tend towards 3. So this means if the number of trials keep on increasing, on an average, it will take him 3 minutes to complete the maze. Okay. Now the third part, how many trials are required so that the rat is able to finish the maze in under 5 minutes? So we need to find the number of trials so that he is able to finish the race in 5 minutes, under 5 minutes. So we have Tn equals to 3n plus 15 upon n plus 1. So time should be such that he is able to complete it less than 5 minutes. So solving this, we have 3n plus 15 should be less than 5n plus 5. This means so n should be greater than 5. So if the number of trials he is making is greater than 5, he would be able to complete the maze, run through the maze in under 5 minutes if he attempts it for 5 times. Okay, now moving on to the next question. Examine the inverse demand curve P equals to 20 upon x plus 1. Show that the demand increases from 0 to indefinitely large amounts as price falls. Okay, the inverse demand function is given to us. P equals to 20 upon x plus 1. So we can derive the demand function with the help of this. So we have x plus 1 equals to 20 upon P. This implies x equals to 20 upon P minus 1. So we have got the demand function with us. Now what they are asking is, you need to show that the demand increases from 0 to indefinitely large amount as price falls. Now, looking at this, what we can see is, if P equals to 1, okay, suppose P equals to 20, X would be 0. And now for P greater than 20, X is less than 0, which doesn't make sense. So at P equals to 20, X equals to 0. Demand cannot be negative, right? And now as price falls, the denominator would increase, the denominator would fall and the whole term would increase, right? So limit X as P approaches 0. So P is falling. So we have limit, this is equal to limit 20 upon P minus 1 as P approaches 0. So this term would be infinity as P approaches 0. So what we can say is, as price falls, the demand increases by an indefinitely large amount. Okay. Now the third part is, find total revenue and show that it increases to a limiting value. Total revenue is nothing but price into quantity. So total revenue is price into quantity. So price was 20 upon X plus 1 into X. So the total revenue is 20X upon X plus 1. Now we need to see how the total revenue, so we need to find limit total revenue as X approaches infinity. So this would be limit X approaches infinity 20X upon X plus 1. This can be written as 20 upon 1 plus 1 by X. So 1 by X would approach 0 as X tends to infinity. So we would be left with 20. The total revenue would converge to the limit 20. I hope this is clear. Now we'll move to the next part. Find elasticity of y with respect to x when function is given by, okay, I'll just write this function, x cube y cube plus 3x cube equals to 2. So we know how to use implicit differentiation. With the help of implicit differentiation, we can find the derivative of y. We can find y dash. And we know elasticity of y with respect to x is change in y by change in x into x upon y. Now, using implicit differentiation, we have 3x square y cube plus 3y square y dash into x cube plus 9x square should be equals to 0. So we can take 3x square common. This would be y cube plus y square y dash x plus 3. This should be 0. Right? So we are left with this equation, y cube plus y square y dash x plus 3 equals to 0. Now expressing this form in term of y dash only, we have expressing this in terms of y dash only, we have y dash y square x equals to minus 3 minus x. So y dash equals minus 3 minus x into y square x. Okay, I hope this is clear. Now, so this is 3x square. I'm just verifying it again. 3x square y cube plus 3y square y dash, then x cube, taking 3x square common, this is y cube. Okay, 3x square common, y square y dash x plus this. Okay, now this should be minus 3 minus y cube. Okay, I'll just make the changes. Okay, we have y dash, this equals to minus 3 minus y cube. So this is minus 3 minus y cube into this. So elasticity would be y dash into x by y, as we have already seen. So change in y by change in x is this. So elasticity would be minus 3 minus y cube y square x into x upon y. So this turns out to be 3 plus y cube upon y cube. So this would be the elasticity of y with respect to x for the given function. Okay. Now moving on to the next question. So we are left with two questions only. Okay. If x is restricted by the condition 0 is less than x is less than 2. So we have this condition. Find the range that y can take given y equals to x minus 1 whole square. Since y equals to x minus 1 whole square, we know y would be always greater than 0 or equal to 0. Right? Suppose x approaches 0, y would approach the value 0 minus 1 whole square, which is close to 1. And as x approaches 2, y will approach the value 2 minus 1 whole square, which is 1. So the maximum value that y can take is 1. And since it lies strictly between 0 and 2, so y won't be able to take the exact value of 1. And when x equals to 1, we have y equals to 1 as well. Sorry, y equals to 1 minus 1 square, this should be 0. So when x equals to 1, y equals to 0. And for all any other values of x lying between this, y would lie between 0 to 1. And 0 is including. You need to make sure about the brackets. 0 is including because x can take value equals to 1. But x cannot take value exactly equals to 0. So 1. So this is the range of y. Okay. Now moving on to the last question. It is given that investment project cost incurs an initial cost of C0. Thereafter, it does not incur any losses and the sum of later profits is greater than the initial loss. Okay, you need to read this condition again. So it's like if you are making a one-time investment and that would be considered as a loss for if you are considering the net present value, and the sum of later profits that you are getting in the later terms is greater than the initial loss. Now we are supposed to show that the project has a unique positive rate of return. Okay, the loss is C0, right? So the expected return would be R is the rate of return, suppose C0, where C0 is negative, plus C1 1 plus R plus C2 R square. So 1 plus R is the discount factor, and suppose we are talking about time period n. So this would be the net present value of the project, right? Now it is given. So suppose f of 0 would be when R is 0, C0, limit f 0 as R approaches 0. Okay, limit f of 0. Okay, just wait a second. First thing is, before doing this, let's look at how the function reacts. So the first derivative would be 0, The second derivative would be, we are differentiating c1 upon 1 plus r. So this, the derivative of this would be with respect to r. This is minus c1 1 plus r to the power minus 2. I'll show how. So the term is like this, and now if you want to differentiate this, it would be minus 1 into c1 1 plus r to the power minus 2. Similarly, solving for the other terms will get, so this would be minus c1 1 plus r to the power minus 2, then minus 2c1 c2 minus 2c2 1 plus r to the power minus 3, then this will keep on going, minus 3c3 1 plus r to the power minus 4, and the last term would be minus of n c n 1 plus r to the power minus n minus 1. Okay, and every value is negative, and it was, so it is given in the question that c1 c2 c3 all are profits till cn. So c1 c2 c3 all these values are positive, these values are positive, and since it is a negative sign, so what we can see is f dash r is less than 0 throughout. So it makes sense as well, because if the discount factor is increasing, the present value of the stream would fall, because if r is 0.1 and if you take r equals to 0.5, the present value would be smaller in case when r is 0.5. Okay, now when we take f of 0 when r is 0, so our stream would become c0 plus c1 upon 1 plus 0 plus c2 upon 1 plus 0 plus till cn. And since it is given in the question, so this is 1 only, this is 1 only. So it is given in the question that, okay, just look at this again. It does not incur any losses after the initial loss, and the sum of later profits is greater than the initial loss. That is this condition. That is C0 is the initial loss, and this is the sum of the later profits. So this sum is greater than the initial loss. So we have f of 0 greater than 0. Okay, is this clear? Now f of r, suppose r is the any other interest rate, as limit f of r as r approaches infinity. This term, it would be c0 plus limit c1 1 plus r as r approaches infinity plus limit c2 r approaches infinity 1 plus r square. Then, but now as r approaches infinity, this term would approach infinity. So c1 by something very high would be close to 0. And similarly for c2, it would be 0, 0, 0 till cn it would be 0. So limit fr as r approaches infinity is c0. And we know c0 is less than 0 because it was the initial loss for us. So what we have is f of r is less than 0 as r approaches infinity. So we have two conditions with us, that is f of 0 equals to is greater than 0 and f of r is less than 0 as r approaches infinity when r is 0. Okay, now what we have is the internal rate of return is that return which makes the net present value. So this is the net present value of the stream equals to 0. So internal rate of return is that rate of return which makes net present value of a stream equals to 0. Now what we can see is, we know these three things. F dash r is falling. So f of 0 is positive, right? So suppose this is the interest rate, this is f of r. At 0, we are getting some positive value. And as r keeps on increasing, f dash r is less than 0. So which means the value of the project should keep on falling. So since it is negative as r approaches infinity, so it would be somewhere here. So there must exist an interest rate, this, which would be the internal rate of return, so that f of 0 is greater than 0 is satisfied, f of r less than 0 is satisfied, and we can also see that f dash r is also falling in this case. Okay, thank you.